Welcome to the Deep Dive. We're the show for you, the curious mind, trying to navigate today's just massive ocean of information. We all want to be clued in, right? To get a handle on complex stuff quickly without drowning in all the details, and be ready to tackle those challenges. That's exactly what we're aiming for here. Today, we're really diving deep. We're looking into data lakes, lake houses, and this really interesting technology called Delta Lake. It seems to be fundamentally changing how we deal with huge amounts of information. Our mission really is to cut through the buzzwords, pull out the key bits of knowledge, maybe find some surprising facts so you feel genuinely informed and, ready for whatever data challenges you're facing. Think of it as your shortcut. Okay, so let's unpack this a bit. We've all heard about data lakes, right? These massive storage spots like HDFS, or maybe more commonly now, cloud storage like S3, Google Cloud, Azure Blob. They're built to just ingest enormous amounts of raw data, structured, unstructured, you name it, scale across lots of machines. But there's also this problem, isn't there? They often become these, data swamps.
Kind of messy, hard to govern, issues with data integrity. And the old data warehouses. Great for structure, but they often struggled with the sheer scale and the flexibility needed for modern big data. So there's this gap. How do we bridge it?
Yeah, and that's exactly where Delta Lake comes into the picture. It was really designed to tackle that specific gap, bringing reliability, performance, and that crucial scalability right onto the data lake storage. This whole idea sort of evolved into what we now call the lakehouse architecture. It's like a fusion, taking the best of data lakes, the scale, the flexibility, and the best of data warehouses, the structure, the reliability, the big goal, a single unified source of truth for everyone who works with data. Delta Lake itself became open source back in 2019 initially as a way to enhance Apache Spark. And it promises some really powerful things like ACID transactions, atomicity, consistency, isolation, durability.
Right, ACID. That sounds familiar from the database world.
Exactly. So imagine you've got, say, two different processes trying to update customer records at the same time. In a basic data lake, that could get messy fast. Conflicting data, unreliable reports. Delta Lake's ACD guarantees act like a traffic controller. Every change is complete and consistent. Your data stays in sync no matter how many things are happening at once. Another core thing is scalable metadata handling, which, when you're dealing with potentially petabytes of data, is absolutely vital. You can't manage that scale without efficient metadata.
Okay, that makes sense. What else?
Then there's schema enforcement and evolution. This is a huge win for data quality. Delta Lake basically makes sure the data being written matches the expected structure, the schema, so no more accidentally inserting text into a number column, stops that garbage in, garbage out problem.
Yeah, good point.
But it's also flexible. You can change that schema over time as your needs evolve without breaking all your existing queries. And maybe one of the coolest features, audit history and time travel.
Time travel, like going back in time with your data.
Pretty much. Ever had a report suddenly go wrong and you have no idea what changed or who changed it? Delta Lake keeps a detailed log of every single change, who, what, when. So for audits, it's fantastic. But that log also lets you query the data as it existed at any point in the past. Yesterday, last week, last month.
Wow.
Yeah, you can see exactly what the table looked like then. It's like a perfect undo button for your data lake. Debugging becomes way easier. It even handles deletes cleverly with things called soft deletes or tombstones, where files aren't immediately gone. They're just marked for removal later by a vacum command.
Okay, so if I'm getting this right, Delta Lake essentially layers database-like reliability, performance, and that crucial version control onto the inherent flexibility and scale of a data lake. That feels like a pretty big deal.
That's a really good summary. Yeah, it's a significant step up.
All right, so that's the what and why. Now, let's get practical.
Yeah.
How do people actually work with Delta Lake day to day? And how does it fit in with all the other tools out there, the basics, I assume, like creating tables, reading, updating, deleting the CRU operations?
Yep, those are all fundamental. You can work with Delta tables either by pointing directly to their storage location, like a directory path, or more commonly in managed environments, you'd access them through a data catalog, something like the older Hive Metastore, or the more modern and comprehensive Unity catalog.
And you mentioned time travel again. That's not something you typically get with standard file formats like Parquet, right?
Exactly. Parquet files are just the data. Delta Lake adds that transaction log layer on top, which enables the time travel. It's a distinct advantage. You also get powerful operations like merge, sometimes called upsert.
Update or insert.
Right. It lets you combine updates and inserts into one atomic operation based on conditions. Super useful for synchronizing data update existing records if they match, insert new ones if they don't.
That sounds efficient.
It is. And there's even a convert to Delta command. If you already have data sitting in Parquet format or maybe even Apache Iceberg format, you can run this command and it'll transform that directory into a Delta table, figuring out the schema and creating that initial transaction log. Makes adoption easier.
Okay, easy adoption is good. But what about fitting into the wider ecosystem? You mentioned catalogs, but what about query engines or streaming platforms?
Great question. Interoperability is key here. Delta Lake is designed to work well with others. Take ClickHouse, for example. We see a few main ways people are using them together. For loading data, you can do one-time bulk loads or set up incremental loading from object storage using functions like S3Cluster or S3Q. There are even tools like ClickPipes building on these for exactly once loading.
Just getting data into ClickHouse from the lake.
Right. Or you can query the data in place. ClickHouse can directly query Delta tables sitting on S3 or other object stores using functions like Delta Lake Cluster. This can sometimes replace tools like AWS Athena, especially for data you don't query constantly, where maybe a few seconds response time is okay.
Querying directly. Interesting. What about catalogs?
There's initial support for integrating with Iceberg REST catalogs, which lets ClickHouse see and query tables managed by Iceberg. The plan is definitely to improve Delta Lake support, further things like integrating the Delta Lake REST kernel for better performance, aiming for write capabilities eventually, and integrating with Delta catalogs like Unity Catalog. That's more of a 2025 roadmap item, though.
Okay, so ClickHouse integration is evolving. What about streaming? That seems like a big use case for lakehouses.
Absolutely. Apache Flink is a major player there. It's a distributed engine for processing streams, both real-time unbounded streams and batches of bounded data. Flink scales massively and provides strong guarantees like exactly once processing, which is crucial for reliable streaming. And it has specific APIs, Delta Source and Delta Sync, to read from and write to Delta Lake tables seamlessly.
So Flink and Delta work well together for streaming pipelines.
They do. And there are other helpful tools, too, like Kafka Delta Ingest. It's a library written in Rust specifically designed for getting high volumes of data from Kafka into Delta Lake efficiently. There's a cool case study from Scribd. They used Kafka Delta Ingest and managed to cut their data ingestion costs by something like 95%. That's pretty dramatic.
95%. Wow.
Yeah.
Okay. Any others worth mentioning?
Yeah, Trino, formerly PrestaSQL, also has a connector. It lets you query Delta Lake tables, often using catalogs like Hive Metastore or AWS Glue. It can also do things like view table history and work with Delta's change data feed feature.
It really sounds like Delta Lake is built to be a central hub, connecting lots of different tools, whether they're for batch processing, streaming, or ad hoc queries. It's a real team player.
That's the goal, making it easier for different systems to work together on the same reliable data foundation.
Okay, that makes sense. Now let's shift gears a bit. Let's talk about keeping things running smoothly. Maintenance, it's maybe not the most glamorous topic, but it's critical, right? Like changing the oil in your car.
Absolutely essential. You can't just dump data in and expect peak performance forever.
So what are the common maintenance tasks for a Delta Lake? I've heard about the small file problem. Is that a Delta-specific thing?
Not specific to Delta, no. It's a common issue in distributed file systems. But Delta Lake provides tools to deal with it. The problem is when you have lots and lots of very small files, maybe under 64 kilobytes or so, each file has overhead network I/O to locate it, opening it. If you have thousands of tiny files for one table, queries slow down.
And streaming applications often create these, right? Little updates coming in constantly.
Exactly. Streaming is a prime culprit. So the main solution Delta provides is the optimize command. Optimize basically repacks the data. It takes those many small files and merges them into fewer, larger files. Think consolidating lots of small envelopes into one big package.
Makes queries faster because there's less overhead.
Precisely. The default target size in Spark Delta Lake is around 1 GB, though Delta Rust might use something smaller, like 250 MB. The goal is fewer, larger files.
Okay, optimize handles small files. What else?
Then there's VCUUM. Remember how Delta Lake keeps old versions for time travel and handles deletes with tombstones?
Yeah.
Well, VCUUM is the command that actually cleans up the physical files that are no longer needed, files from versions older than the retention period, or files marked for deletion that are past their grace period. There are retention settings, usually defaulting to keeping logs for 30 days and deleted file references for about a week, but you can configure these. VCUUM enforces those policies.
So it keeps the storage footprint from growing indefinitely.
Right. And finally, you can often automate some of this using table properties, TBL properties. Things like delta.auto-optimize.optimize-write or delta.auto-compact can trigger optimization processes automatically.
Automated preventative maintenance. Nice.
Exactly.
Okay, so that's the basic upkeep. But what about really tuning performance? Going beyond just cleaning up. I imagine there are trade-offs, right?
Right. There absolutely are. Often you're balancing the needs of the people or processes writing the data the producers versus those reading it the consumers. You might tune for faster data ingestion, which might make queries slightly slower, or you might optimize heavily for query speed, which could add a bit of overhead during writes.
How does Delta help with query performance specifically?
A key mechanism is data skipping. Delta Lake automatically collects statistics about the data within each file, things like the minimum and maximum values for columns, the number of records, null counts. These stats are stored right in the transaction log, the metadata.
Okay.
So when a query comes in, say asking for records where order date is within a specific week, the query engine can look at the min-max stats for order date in each file's metadata. If a file's entire date range falls outside that week, the engine knows it doesn't even need to open or read that file. It just skips it.
Ah, clever. It avoids reading unnecessary data based on metadata.
Exactly. It can drastically reduce the amount of data scanned, speeding up queries significantly. You can even control how many columns get these detailed statistics collected using a property like delta.dataskippingNoMindexedCalls.
That sounds powerful.
Yeah.
Is there anything more advanced?
Yes, there's a technique called Z-ordering. It's a bit more advanced, a form of multidimensional clustering. Imagine you frequently filter by both country and product category. Z-ordering tries to physically arrange the data on disk so that rows with similar values for both those columns are located close together, ideally within the same files.
So it makes the data skipping even more effective for common query patterns.
Precisely. If the data is Z-ordered by those columns, a query filtering on both is much more likely to skip large chunks of irrelevant files. And on the automation side, particularly in Spark environments, you have features like auto-compaction. This can actually run optimizations like compacting small files while data is being written with just a small impact on write latency. There's also optimized writes, which adds an extra processing step before writing the data. It shuffles the data in memory to group it better, aiming to write fewer, larger files right from the start, rather than cleaning them up later with Optimize.
So proactive optimization during the write process itself.
Correct. And there are other advanced features for quality and efficiency we should touch on. We mentioned deletion vectors briefly.
Right, the merge on read idea.
Yeah. Instead of rewriting a whole data file just to delete or update a few rows, which is expensive, deletion vectors are small sidecar files that just mark specific rows as deleted or updated. The query engine then combines the original data file with the deletion vector information when it reads the data. The actual file rewrite can be deferred until a later optimized run, making updates and deletes much faster, especially for transactional workloads.
That sounds like a huge performance boost for certain operations.
It can be. Then there are generated columns. These are columns whose values are automatically calculated based on an expression you define using other columns in the table. For example, you could have a timestamp column and define a generated column for year that automatically extracts the year. It ensures consistency and saves you from having to calculate it manually during ingestion.
You can override them.
Nope, they have an always constraint. You can't insert your own value. And finally, don't forget basic but important things, like check constraints to enforce data quality rules. For example, ensuring a price is always positive, and using comments on tables and columns for documentation makes the data much easier to understand and trust.
Okay, so it really is about more than just storage. It's about building in intelligence, automation, and controls to keep the data clean, consistent, and fast for whoever needs to use it downstream, working smarter.
That's a perfect way to put it.
All right, let's zoom out again. We've talked about the core tech, the operations, the maintenance. How do organizations typically structure their entire data ecosystem when using Delta Lake? How do they ensure reliability, security, traceability at scale?
A very common pattern you'll see is the Medallion architecture. It's a design philosophy, really, for organizing data logically within the lakehouse.
Medallion, like bronze, silver, gold.
Exactly. It's a layered approach where data gets progressively refined as it moves through the layers. You start with the bronze layer. This is where your raw data lands, usually straight from the source systems, maybe Kafka topics, database dumps, raw files. It's typically immutable, unchanged from the source.
Kind of the landing zone, the historical archive.
Right. Crucial for reprocessing, debugging, lineage tracing. But you generally don't let end users query this directly. It can be messy. Then data moves to the silver layer. Here, it gets cleaned, filtered, maybe augmented with other sources, conformed into a more consistent business-level view. Think curated, validated data sets.
More usable, getting closer to analysis.
Definitely. And finally, you have the gold layer. These are highly refined, often aggregated data sets, specifically tailored for business intelligence, reporting, analytics, or machine learning use cases. Gold tables are optimized for consumption. They might be aggregated sales summaries, feature tables for ML models, things like that. They could be physical tables or sometimes just views on top of silver data.
And this applies to streaming too.
Absolutely. You can implement this as a streaming medallion architecture. Data flows in real time through bronze, silver, and gold transformations. Companies like DoorDash use this pattern with Kafka, Flink, and Delta Lake to handle massive daily data volumes with low latency.
Okay, that layered approach makes sense for organizing the data flow. But how do you manage governance? Security, trust, knowing who did what?
That's where robust lakehouse governance comes in, and it's critical. It involves several key pieces. You need strong access controls, obviously. You need data catalogs and metastores to know what data you have. Audit logging is essential for tracking activity, monitoring for performance and health, mechanisms for secure data sharing, tracking data lineage, and enabling data discovery.
That sounds like a lot to manage.
It is, but the architecture helps. The medallion layers help manage data lifecycle and retention. Maybe you keep raw bronze data longer than aggregated gold data. Delta's table properties, like delta.log retention duration, help control the history within each table. A really important concept here is thinking in terms of data products.
Data products, what does that mean exactly?
Think of a data product as more than just a table. It's the combination of the data itself, the code used to create it, the metadata describing it, and maybe even the infrastructure needed to run it. The ideal is a purpose-built data product, a data set that's curated, high quality, well-documented, and immediately usable for a specific purpose without requiring consumers to do complex joins or cleaning themselves.
So delivering value directly.
Right. And building trust in these products relies heavily on having clear metadata, traceable lineage, published data quality metrics, and good observability across the whole pipeline. For managing who can access what identity and access management IAM, you typically define roles like developer, analyst, business user, and use access grants, maybe tied to cloud IAM systems like AWS S3 access grants, often using organizational patterns like specific prefixes in your storage for different data sensitivities or teams.
And classifying data sensitivity.
A simple but effective mental model is the stoplight pattern. Green data is low sensitivity, general access. Yellow is restricted, needs specific permissions. Red is highly sensitive, maybe PII or financial data with very tight controls. Regulations like GDPR, CCPA, SOC2 often guide these classifications.
Okay, so governance covers access, lifecycle, quality. What about understanding the flow, the lineage part you mentioned?
Crucial. This relies on good metadata management and data lineage. A centralized catalog is key here. We mentioned the Hive metastore earlier. But increasingly, especially in the Databricks ecosystem, but also aiming for wider reach, there's Unity Catalog. Unity Catalog acts as a universal catalog not just for tables, but for AI assets too. It provides a consistent governance layer across tables, views, notebooks, ML models, dashboards, the whole data estate. It uses a 3-level namespace, catalog, schema, table, which offers more organizational flexibility.
So it's a central place to define and manage everything.
Exactly. And lineage tools track how data moves from source systems through transformation jobs like Spark jobs or Flink jobs into intermediate tables and finally to the consumption layers, those gold tables or data products. This helps you understand dependencies. If I change this upstream table, what downstream reports or models will be affected. It's vital for impact analysis, debugging, and auditing. There are standards emerging like Open Lineage to capture this operational metadata consistently across different tools.
It really paints a picture of a much more controlled, transparent, and trustworthy data environment. Knowing where data came from, what happened to it, who can see it, that fosters confidence.
That's precisely the goal. High trust across the organization.
Okay, one last big topic. Sharing data. This feels like a perennial headache, right? Getting data securely between different departments or even completely different organizations, maybe across different clouds. The old way, exporting files, emailing CSVs, setting up FTP drops. It's often complex, costly, and creates multiple copies of the data, doesn't it?
Oh, it's a huge pain point. You called it the distributed synchronization problem. It's exactly that. You've got the complexity of setting up and managing all those export pipelines. You've got the cost egress fees for data leaving one system, ingress fees for it entering another. You end up with multiple versions of the truth scattered everywhere. And the processes are often brittle. If one export job fails, data gets out of sync. It's a mess.
So how does the Delta ecosystem address this?
With something called the Delta Sharing Protocol. This was specifically designed as an open standard to tackle this data sharing problem head-on.
Open standard, so not tied to one specific vendor.
Correct. It's vendor agnostic. The core idea is to let you securely share live data directly from your Delta Lake tables with any recipient on any platform that supports the protocol, crucially without having to copy or replicate the data first.
No copying. How does that work?
Instead of setting up export jobs, you define shares on your Delta tables. A share basically grants controlled read-only access to specific tables or partitions. Recipients authenticate, usually with a secure bearer token, and they can then directly query the shared tables using clients that understand the Delta sharing protocol. They get the table metadata, schema, properties, and can query the data as it exists in the source table.
So they're always querying the single source of truth.
Exactly. No data movement, no copies, no synchronization issues. The recipient always sees the live, up-to-date, or time-traveled, if allowed, version directly from the provider's lake. And there's broad client support already, libraries for Spark, Pandas, Rust, Go, C++, Mez, connectors for Power BI, Tableau, and more being built.
That sounds much simpler.
Yeah.
And more secure.
It is. It dramatically simplifies cross-team or cross-organization collaboration. And this ties back into another concept called uniform or universal format from Databricks. Uniform allows a Delta table to automatically generate the metadata needed for other formats like Apache Iceberg and Apache Hudi. So a single Delta table can be read natively by clients expecting Delta, Iceberg, or Hudi formats, further boosting interoperability. Delta sharing works on the core Delta format, but Uniform helps broaden the reach even further for clients that might not directly support Delta sharing yet, but do support Iceberg or Hudi.
Wow. So instead of constantly shipping data copies around and worrying if they're stale, you're basically giving controlled, secure, real-time access directly into your authoritative data.
Yeah.
That really does feel like a game changer for making data more accessible and collaborative.
It fundamentally changes the dynamic of data sharing.
So thinking about that, what are some of the maybe non-technical hurdles? If the tech makes it easy not to copy, what stops organizations from just sharing everything?
That's a really insightful question, because you're right, the protocol removes the technical friction of copying. But the biggest hurdles often become organizational and related to governance. You still need to decide what data is appropriate to share. You need to define clear data contracts. What does this shared data represent? What are the quality guarantees? What's the support model? And you need robust processes for managing access policies, approving recipients, and auditing usage. It shifts the focus from managing complex ETL pipelines to managing data agreements, trust, and governance policies. That requires collaboration and clear ownership, which can sometimes be the harder part.
Right, the human element, the process element.
It makes sense.
Okay, what a journey. We started with the challenges of those early data lakes, then dug into how Delta Lake provides that solid foundation with ACD, schema enforcement, time travel.
Yeah, and then how it connects with tools like ClickHouse and Flink for different workloads.
Right, and the practicalities of maintenance, optimize, vacuum, keeping things healthy, plus tuning with data skipping and Z-ordering.
Then the big picture view, the Medallion architecture for structure, and the critical importance of governance, lineage, and data products.
And we wrapped up with Delta sharing, that open protocol aiming to kill the data copying nightmare, while also acknowledging the governance side of sharing. So here's a thought to leave you with. Imagine what becomes possible in your own work, your own organization, if the chaos of data management starts to fade, if it's replaced by clarity, controlled access, and a genuine single source of truth. What new questions could you ask? What new insights might surface if your data wasn't a barrier but actually worked for you, seamlessly, reliably across all your tools? We definitely encourage you to explore these ideas more. Check out the open source Delta Lake project, look at the docs, the GitHub repos for connectors like Kafka Delta Ingest or the Flink connector, engage with the community. It's a really active space. And please keep bringing us your complex data challenges. We love diving into this stuff. Thanks for joining us on The Deep Dive.